Hi, welcome to our 24th lecture in Graduate Combinatorics. Today we'll continue discussing the topic of trees. As you recall, last time we introduced the notion of a tree in the previous lecture, and we say that a graph is called a tree if it is connected and has no cycles. So automatically a tree is a graph that is simple. It cannot have any loops or multiple edges because those would be cycles. And the graph is also connected. So on the screen, you see various examples. So you see unlabeled trees when n equals 3 over here. And then when n equals 4, you see the trees, the unlabeled trees over there. N equals 5, I draw them, and I draw some more examples for n equals 6 in the right column. And last time we proved this proposition, which states the following: if T is a tree with n vertices, then it has two properties. So one, if n is greater or equal to 2, then T contains at least two leaves, which are vertices of degree 1. Okay, so you can see in all these examples, but that is true in general for any tree with at least two vertices. And second one is that the number of edges in this tree, in any tree, equals n minus 1. So if you have n vertices in a tree, you know the number of edges is n minus 1. So we proved these results last time. And I think I didn't mention it last time, but the assumption of finiteness, the fact that you're talking here about a finite graph on n vertices, this is crucial for the existence of two leaves, because you can have this example of an infinite graph like this, where the vertices are all the integers. So you will have the integer k being adjacent to k plus 1 and to k minus 1. So you'll have the vertex set to be all the integers, and k will be adjacent to k plus or minus 1 for any k integer. And this graph, it has, it has an infinite number of vertices. It doesn't have any cycles, and it's connected, but it doesn't contain any leaves. And this graph is also an example, an extreme example, for the previous propositions, which we proved in some previous lecture, that if a finite graph has minimum degree at least 2, then it must contain a cycle. This graph has minimum degree at least 2, but it doesn't contain a cycle, because these ends do not meet. Okay. Now, today we'll talk more about other properties of trees, and let's give the following characterization of a tree. So this is a theorem. So let's say let gamma be a graph on n vertices, and the following statements are equivalent. One is that gamma is a tree. Two, gamma is connected, is connected and has n minus 1 edges. 3, gamma is acyclic and has n minus 1 edges. And 4, for any vertices, for any vertices x and y of gamma, there is a unique path between x and y. So before we give the proof, let's just pause for a second and figure out what this is. Remember that a tree, so a graph that is a tree, it has to be connected and acyclic. So if you look at the first part of the theorem says that the graph is a tree. So that means, again, connected and acyclic. And the second and the third part, just take one of these conditions and replace it by the number of edges. So second part is gamma is connected and has n-1 edges. So you replace the acyclicity with this condition. And similarly, for 3, you replace the connectivity by this condition that gamma has n-1 edges. And part 4 is a little bit different. It's a kind of global type of condition again, which requires that between any two vertices, there is a unique path between them. Okay. So let's see how do we prove. So I'll prove some of these implications and leave some for you to do. I know in some of your comments, you like me to flesh out the details for every example, but I think it's very useful for you to work it out by yourselves. And I'm happy to answer any questions you have if you work out the examples or the leftover proofs from these notes. I'll be happy to talk to you. Okay, so let's see. Let's say 1 implies 2. I think we pretty much did it because it was done, it follows from the previous proposition. Proposition that any tree on n vertices has n-1 edges. Okay. Now let's see, go a little bit circular. Let's see 2 implies 3. Okay. So 2 implies 3. What do we have to assume? So we assume that gamma is a connected graph with n vertices and n-1 edges. And we want to prove that gamma is acyclic. So you can go by contradiction. So let's assume that gamma contains some cycle. And what we do is we delete an edge from that cycle. So delete and you know, if it you know, the key thing is that the resulting graph this new graph is still connected, because if you needed that edge that you deleted, you know, you can have your graph being something like this, okay? And let's say you delete this edge from a cycle. That doesn't destroy the connectivity because, okay, let's say we had some vertices for which the path, the short path between them went through that edge. So let's say you have this vertex A here and this vertex B here, and a path between them would go through that edge. If we delete that edge, because that edge is in the cycle, you can use the other part of the cycle to go from A to B. So A and B would still be connected by a path. So now you can continue this process until, so continue deleting edges from cycles until we destroy all the cycles of gamma. Okay, the resulting graph has n vertices because we don't delete vertices, we just delete edges, and is still connected by our previous argument, and also acyclic, because at this point we have removed all the cycles. But because it's connected and it's acyclic, that implies that this graph is a tree, but is a tree on n vertices. Therefore, it must have n minus 1 edges. But what did we do? We started with a graph with gamma that had n minus 1 edges, and we deleted some edges and ended up with a graph that is a tree and has n minus 1 edges. So in the end, you know, we didn't have to delete any edges. So therefore, gamma must be a tree. Okay. All right. So that's 2 implies 3. Let's do 3 implies 1. Now for this one, I don't think I introduced this notation, this definition last time. So a tree is a connected graph that is acyclic. So let me recall it here. Tree is connected and acyclic. But now if you have a graph that is only acyclic, that's called a forest. So a forest is an acyclic graph. Okay. So a forest, if a forest is connected, then automatically is a tree. But a forest, if it's not connected, then it has at least 2 components, and each of its components are must be connected, and each of the components must be acyclic from the definition of the forest, and that makes each of the component a tree. So a forest is nothing more than a disjoint union of trees. And if the forest is connected, then you have just 1 tree. But if the forest is not connected, you have two or more trees. So that's what a forest is. Okay. So now, when we want to prove 3 implies 1, so let's see what 3 is. 3 is that gamma is acyclic and it has n minus 1 edges. And we want to prove that gamma is connected, which is that gamma is a tree, essentially in this case. So assume that gamma is acyclic with n minus 1 edges. We want to prove that gamma is connected. In some sense, this is the same as the proof of 3 equivalent to 2, if you want. Okay. All right, so we have gamma that is acyclic, so it can have various components. So let's just call them, let gamma 1, blah, 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 gamma k be the components of gamma, and denote by nj the number of vertices of gamma j for j between 1 and k. So clearly, because these are the components, every vertex has to be in some component. So clearly, n1 plus blah, blah, blah plus nk must equal n. Those are all the vertices. Now, what we're going to do is count edges. And because, so we can, for j between 1 and k, gamma j is a tree because it's acyclic since gamma was acyclic, and it's connected because any component has to be connected. And therefore has nj minus 1 edges. Okay, so each gamma j has nj minus 1 edges. So now what happens here is that you have this situation with, okay, this is gamma 1. This is gamma 2, and so on. And this is, let's say, gamma k. So there are no edges in between. So there are no edges between them because that's what, you know, they will contradict the definition of a component, which is a maximal connected subgraph. And so the number of edges in gamma is the number of edges of gamma 1 plus the number of edges of gamma 2 and so on. So therefore, gamma has n1 minus 1 plus blah, 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 plus nk minus 1 edges, which is the same as n1 plus blah, blah, blah plus nk minus k, but n1 plus nk equals n, so you replace it here, so this becomes n minus k edges. So gamma has n minus k edges, but our hypothesis also told us that gamma has n minus 1 edges. So thus, n minus 1 must equal as n minus k, which means that k equals 1. Hence, k equals 1 means there is one component in gamma, and that means gamma is a tree. Okay, and that's it. All right, so for the last one, 5 page here, let's do the equivalence between 1 and 4. Okay. So let's assume that gamma is a tree. So then let x not equal to y be two vertices in the vertex set V. So let's say gamma is vertex set V and set edge set E. And now because gamma is connected, there is at least one path from X to Y. Okay. And now we'll argue that actually because, so here's the kind of the more subtle part of the proof, because gamma is acyclic, we cannot have two paths from X to Y. Why is that? Well, here's how it would work. If you have X here and you have Y here, let's say you have some path like this, and then the path from another path from X to Y could start the same way as that one, but maybe go in different ways, something like this. Should maybe draw it with a different color. Let me try a different color. So maybe it's like this. Okay, something like this. So what happens? You have these paths could overlap. So if it's a proof by contradiction. If you have two paths from X to Y, this path could overlap, and then you can mark down as you go from X to Y on these paths. You can mark down the last point where these two paths are the same. And in that situation, this is it, okay? Because these two paths, the black path and the gold path, these two paths are distinct, there has to be a point at which one edge in one path is different than one edge in the other path, okay? And then after this step, you can mark down the first step where these two paths become equal again, which is this one. And now what you have is, you have these two vertices which are equal, but in between them, the black path and the gold path, they do not overlap. They do not have vertices or edges in common. So that creates this cycle. Okay. So that's the argument, showing that there's a unique, you have at least one path, but you cannot have two or more paths between X and Y. So hence, there is a unique path between X and Y. Okay. Now the other argument, so this is the argument for 1 implies 4. And now let's quickly do 4 implies 1. If you have a graph that has the property that between any two vertices there is a unique path, then clearly gamma must be connected. Okay, because for any two vertices there is a path between them, so that's good. And the other one is by contradiction, if gamma contains a cycle, you can, it's easier to just draw it. Let's say you have a cycle like this. Then you can take two vertices on that cycle, X and Y, and you can, from X to Y, there are two paths that you can go. You can go this way, and you can go the other way from X to Y. So then if X and Y are two vertices on that cycle, then there are two XY paths, which is a contradiction. Impossible. Okay, I put these two swords, in fact. Okay, so that's basically the argument that the graph is connected and acyclic. Okay. Now, we talked last time about this result of Cayley. So this theorem, which is attributed to Cayley, but like I said, it was proved by Borchardt, I think 1860, I think, and Cayley, 1889. And it says that the number or labeled trees on n greater or equal to 2 vertices, I think it works on 1 as well, vertices is n to the power n minus 2. Yeah, I think also it can put 1 here. Okay. So, and I gave you a description last time about the difference between labeled versus unlabeled. So unlabeled, let's say when n equals 4, okay, have one path and you have 1 star. One star this way. So you have two unlabeled trees on n vertices, but if you do labeled, then, for example, I can label 1, 2, 3, 4, and this one, it's actually different than 1, 3, 2, 4, because the edge set of these two trees are different. So the edge set of the one on the top is 1, 2, 2, 3, 3, 4. The other one is 1, 3, 2, 3, and 2, 4. Okay, and so you can play on like this with all, try to figure out how many are of this form, and you can also the stars are easy to figure out because here there are going to be 4 because it just depends on what vertex you put in the center of the star. So there are going to be 4 of these, and if you want to count the other ones, there will actually be 12 of them. And it's, you see, like the 2 vertices here, you can do the count. It's not too difficult. So you can get 12 and you get 16. And this agrees with, 4 to the power of 4 minus 2, which is 16. Now, there are several proofs of this result, and we'll give a couple of them. The first one, it's done via what are called Prufer codes. Okay, so a Prufer code is a way of encoding a tree, a labeled tree on n vertices, using a word. And this is due to a German mathematician by the name Heinz Prufer. And it's a useful, very useful construction, especially in computer science, to store the information of the tree. So again, let's assume that the tree that we're talking about, so we're talking about T is a tree with vertex set 1 all the way up to n, which we denote by this n between. So in order to encode the tree, it's the same thing as knowing the n minus 1 edges. If you know the edges, then you're done. And we'll always work with this set of vertices. You can label them differently if you want, but it's essentially the same as 1 to n. Okay. Now the Prufer code, I will show it to you. I'll define it by a bunch of examples, but the code of this tree, we'll denote it by A of T will be a word of A1, blah, 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 AN minus 2. It's a word, it's an ordered n minus 2 tuple where the entries A1, blah, 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 AN minus 2 come from the set, from our set N. Okay. And I'll show you in terms of some example how this is constructed. And then we'll prove the more difficult part, which is that the collection of labeled trees on n vertices and the collection of all these ordered n minus 2 tuples with entries coming from the set 1 to n are in a bijection. So basically every tree is going to give me a unique Prufer code, and any code corresponds to a unique tree. And therefore, because these two sets are in a bijection, the number of labeled trees on n vertices will equal the number of these ordered n minus 2 tuples with entries from the set 1 to n. And that number is n to the power n minus 2. Okay. So let me show you some examples of how this is defined. And it can seem a little bit strange because I told you that we have n vertices and we have n minus 1 edges, but we are going to take care of all the information, but by using just n minus 2 symbols. Okay. All right. So let's do some. I'll give the definition by an example first. So let me take one of these purple ones. 1, 2, 3, 4. So we had this tree. So here, this is our first tree, let's say T1. And here, n equals 4. And the procedure is the following. First, at the first step, you look at the smallest leaf in this tree T. And so smallest with whatever ordering you can put on, you want to put on your vertices. So in this case, just an usual ordering. So the smallest one is 1. So I call that one B1. And now I define the first entry in my Prufer code, the A1 entry, is the neighbor of B1. Okay. So first we look at the smallest leaf, which is B1. It's this vertex here. And then A1 is the neighbor. So maybe I do the B's here. And I do the A's under it. No, sorry. Okay. And so this is 1. So I'll write them from right to left. So the first entry in the B is a 1. And the entry in the A is going to be 2. And so in this case, A1 is 2 because that's a neighbor. Okay. Now we look at the tree, which is obtained by just removing, getting rid of that leaf 1. So we have now a new tree. Let's call it T1 prime. We have 2, 3, 4, and we repeat the procedure. We look at the smallest leaf in this new tree T1 prime, and we denote this by B2. And in our situation, B2 is 2, so we can put it here. And what is the, you would define A2 to be the neighbor of B2. Okay, and in this situation, that is going to be, A2 is going to be 3. So we put there 3. Okay, and now we are going to stop because we have reached, so what do we have now? We have this table, and the Prufer code of this tree, essentially the Prufer code of that tree is going to be denoted by this A of T1, consists of just the entries 2 and 3. And it has length, you can see, it has length n minus 2, which equals 2. Okay. It's not at all clear why, this is, gives me all possible, why this is going to be a unique correspondence. I mean, from the order n-1 tuples to the trees, but let's do some more example, and maybe that will to get more familiar with it. Okay, so let me give you the example that, so let's go through one example from the notes. So let's see. We have this tree. Okay, so in this situation, I'm going to have n equals 9. And these are the vertices 1, 2, 3, 4, 5, 6, 8, 7, 8, and 9. Okay, and now I will just do the procedure on the table. So I'll have the B on this row, and I'll do the A's on the row below it, and kind of with the index going from right to left, starting at 1. Now, what is B1? So B1, again, is the smallest leaf. And you look at the leaves, and the leaves are 5, 7, 2, 3, and 4. So the smallest of them is 2. So we put as B, entry 2. And then what is A? A is going to be the neighbor of that leaf, which is 8. Okay. Now after that, that 2 disappears. So you ignore 2 from now on. So I'll just put a purple over it. It's purple listed. Now we do the same thing. What is this? The B2 will be the smallest leaf in the remaining tree, and that one is 3. And so that is this one here. And what is A2? That's going to be 6. That's its neighbor. The next leaf is 4. So that's 4. And what is its neighbor? It's also 6. And then now we still have just, we have to be a bit careful because now 6 has become a leaf, but we have 6, 5 and 7 as leaves, so 5 still is the smallest, and its neighbor is 9. And now we have as leaves, so 5 has become a leaf. Now we have as leaves 6, 9, and 7. So 6 is the one that we get rid of, and that gives us an 8. So we have this 6 over here. And now the two leaves that are there are 7 and 9. So that's 7, and that's 9. And we end up now with 7 is not there anymore. So you have this tree with 1, 8, 9. And the smallest leaf there is 1. And his neighbor is going to be 8. We have n equals 9 vertices. And this is of length n minus 2, which is 7. And in this situation, let's call this tree T2. Prufer code of this tree is 8, 6, 6, 9, 8, 9, 8. Okay. Let me see. Somehow I have an A6 to be 1. Okay, so let's just kind of go over it again. So we deleted 2. That's okay. You end up with 8. Okay. Deleted 3, you end up with 6. Deleted 4, yeah, you get 6. And then we deleted 5, and we have a 9. And then our, okay, yeah, there's the 7, when we delete it, there should be a 1 here. This is a 1. I'm sorry, that's an 8. Okay, so that's a 1. Okay, sorry about that. Now, okay, so so the last one that was deleted here as a purple, it was this one, it was the 1. Okay, you have the 1. Now, what do you observe here? What are the edges of this tree? Let's start with the first example on the top. What are the edges of our tree? So if you look at the two columns, we have 1, 2. That's the first edge, and then what is going to be the next the next edge is going to be 2, 3. That's the next edge. Now there is one edge that is hidden there. If we continued, so if we continue the procedure one more step, if we continue this procedure one more step here, we, at this point, after we deleted the leaf 1 and then the leaf 2, we have the graph, which is just 3 and 4. And by our definition, B3 should be the smallest leaf that's available, but the vertices that are left are just 3 and 4, so the smallest leaf is going to be 3. And then the neighbor adjacent to it is 4, okay? So you notice here that the neighbor, the vertex 4, is never going to be deleted in this, is never going to be deleted in this procedure, because you always have at least 2 leaves to pick from to delete. And 4 is the largest, so it will never be available to be deleted as a leaf, unless at the end, when you have just 2 vertices remaining. That's why 4 will always be here. And similarly, you can do the same argument for any tree, but let's do it for this other tree below. At the end, we end up with 8 and a 9. And what is the smallest leaf there? Well, clearly it's 8. And what is the vertex adjacent to it is 9. So you see, technically speaking, this Prufer code is actually it has actually length. So I'll put here a 9 at the end, and I'll put a 4. You can think of it as having a 4 at the end. But you'll always have, you can, the Prufer code, you can think of it as an n-1 tuple. So as this one, so you have a1, blah, 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 a n-2, but the last entry is always the same. The last entry is always going to be n, which is a n-1. So that's why you can just ignore that last entry, and you can just use just these n-2 entries that you have here. Okay. Okay. So this is the procedure. Let's kind of make it a bit formal now, and then I'll show you why you can reverse it. So again, let's say we have a tree, and let's take n greater or equal to 3 vertices, because I need something in it at least to delete. And from it, I show you how you can define a1 blah 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 a n-2, which is at, and this is called the Prufer code of t. So this can be seen as a definition of the Prufer code. Okay, and again, it's in steps. So like I said before, b1 is the smallest leaf in t, and you can define a1 to be the neighbor of b1 in t. And then at step 2, we get rid of b1. So we need another tree. So let's just call it, so I can call t to be, let's call it t, and you can think of it t1. Let's call t2 to be the tree t1 minus this leaf b1. And in this tree, we do b2, the smallest leaf in t2, and you can define a2 as the neighbor of b2 in t2. The first operation and the second operation are well defined because we are deleting, at each step, we're deleting a leaf from a tree. And by an argument from the previous class, whenever you do that, the graph that is remaining is also a tree. So you can continue like this. And let's say the n-2 steps, okay? We have, we end up with, so let's say T1 here, T equals T1 has n vertices. T2 has n-1 vertices. Okay, so T2 here has n-1. And if you go like this, you end up Tn-2. It's a tree on 3 vertices obtained in this fashion. And here we can look at this tree and we can define Bn-2 to be the smallest leaf in Tn-2, and then you can define An-2 to be the neighbor of Bn-2 in Tn-2. Okay. So yeah, keep in mind this this procedure. So this is how you define the Prufer code. This is the way to go from the tree to this n-2 to the Prufer code. And this is a proposition. That so for let's say n, let n be greater or equal to 3. The correspondence T maps to A of T is a bijection between the collection of labeled trees on n vertices and words of length, or n minus 2 tuples, okay, so over the set or the alphabet n, okay. And so to show this, essentially what we have to show is, the way to prove this is to show that if you give me any, so it's clear that from a tree you get this is well defined. You get some word n minus 2 tuple of with entries in the set 1 to n. But what I want to show is that this function has an inverse. So basically, if you give me some n tuple here in the Cartesian product n times blah blah times n minus 2 times, then there is a unique tree which is labeled tree on n vertices. So let's call this A, with A of t equals A. Okay, and the construction will show that t is unique. Okay, so now how do we construct this this tree? So in our situation, we have the vector A. So we have A1, we have A2. This is given to us, an minus 2. And by our construction, we also have an minus 1. We know what an minus 1 is. This is exactly n. Okay. So the question here is, what are the b's? So what do we put here? What is b1? What do we put here? What is b2? And what do we put here all the way to the end? What are these values? B1, B2, all the way to Bn minus 1. Because if you show that these values are unique, and so on, then the collection of edges, the edges that you have here, B1, A1, B2, A2, Bn minus 1, An minus 1, and all these other ones, these are going to be the n minus 1 edges, okay, of the tree T. Okay. So how do we get this information? Well, we look here at the way B1 is chosen, and we reverse it. So when B1 is chosen in this procedure of the Prufer code, all the vertices in n without these values A1, A2, and so on, An minus 2, An minus 1, were available. And so B1 is the smallest one from them. So what you can say is that B1 is actually the minimum over all x with x in the set n minus A1, An minus 2, An minus 1. Okay. Now, once B1 is gone, B1 is a leaf, it basically never appears anywhere else, then we have this smaller tree, and in that smaller tree, B2 is the smallest leaf, and by a similar argument, B2 is chosen. So when you have all these vertices in n minus B1, A2, An minus 2, An minus 1 available, and B2 is the minimum of these values. Okay. And so the pattern continues like this. So in general, BK is actually the minimum over all x with x in the set n minus the sets that were deleted already, B1, vertices that were deleted already, B1, BK minus 1, and the other ones that are, you know, AK all the way to An minus 1. Okay. And this way we produce, you can go all the way to Bn minus 1, similarly, and these are the edges of the tree. So I'm out of time for this lecture, but I'll go over it again in the next lecture, and I'll do some examples to show how again how this correspondence between labeled trees and Prufer codes go.